So we learned to assign oxidation states, and now we're going to learn how we can use the oxidation states to identify redox reactions. So we can define redox, oxidation and reduction, two different ways: by looking at the oxidation state or by looking at whether electrons are lost or gained. So an oxidation is an increase in the oxidation state or a loss of electrons. A reduction is a decrease or a reduction in the oxidation state. The oxidation state goes down, it's reduced, or a gain of electrons. So in this reaction here, we have two nonmetals reacting, and so we can't use charges and look at electrons being transferred because there aren't any ions here. So we use oxidation states. We have an element, carbon, and an element, sulfur. So they both have 0 for their oxidation state. In this compound, carbon disulfide, we say Fe765, there's no fluorine, there's no hydrogen, there's no oxygen, there's no group 7, we're running out of things, but there's group 6. Sulfur's group 6, so it gets what it wants, it gets to be -2. The carbon has to be whatever is needed to make up the difference, so the carbon is +4. So we assign the oxidation states, and then we can look at what happened, how they changed. So carbon went from 0 to +4. That's an increase in oxidation state. Carbon is being oxidized. The sulfur went from 0 to -2. That's a reduction in the oxidation state. That's a reduction. So we identify that there is redox occurring here. Any questions? Yeah.
So sulfur lost electrons. Oh no, it gained electrons.
Yeah. Those electrons are just so pesky in so many ways. They have a negative charge, and adding negatives is just always makes your brain flip around. Yeah. Any other questions? So let's use oxidation states to identify the element that is oxidized and the element that is reduced in the following redox reaction. So with redox reactions, we're looking at the individual elements. So we're not going to say that nitric acid is reduced or oxidized. We're going to say that one of the elements in it is oxidized or reduced. And it's possible for there to be more than one occurring. I don't think we're going to run into any in this class, but it's possible. So the first thing we're going to do is we're going to go through and assign oxidation states to every element. So here's tin. What's its oxidation state? 0. It's an element by itself, no charges, 0. Here we have nitric acid. We have 3 nonmetals. So we've got that order, Fe765. There's no fluorine, but there's a hydrogen. Hydrogen gets its pick of oxidation state. These elements are always going to pick an oxidation state that is the same as their ion charge if they were an ion. So what does hydrogen want to be? +1. Well, we still have 2 left, so we'll continue on down the line here. After hydrogen is oxygen, and we have oxygen. What does oxygen want to be? -2. So oxygen is -2. We figure out what nitrogen is because all of the oxidation states have to add up to the overall charge. This is a neutral molecule, so all the oxidation states have to add up to 0. There are 3 oxygens. They are each -2. This math here is not hard, but it can mess you up still. So we have a total of -6, and this is a +1. The coefficient of 4 has nothing to do with this. We're just looking at the one molecule. -6 and +1, how do we get that to add up to 0? Must be +5, right? So I'm going to erase these because we don't need those. So the nitrogen is +5. Anybody have any questions about that? Over in the products, here we have an ionic compound. So with ionic compounds, it's easiest to just look at their charges because those are the oxidation states. So what is the charge on an oxide ion? -2. And there are 2 of those, so what's the charge on this tin ion? +4. And we learned how to do that when we learned how to name this. This would be tin 4 oxide. Here we've got NO2. Again, we have to use Fe765. No fluorine, no hydrogen, but there's oxygen. Oxygen gets to pick. Oxygen always picks -2. What does the nitrogen need to be? +4. The nitrogen is not automatically going to be the same thing as it was over here. In fact, it's often going to change. So we have 2 oxygens. They're each -2 in oxidation state, so that one nitrogen has to be +4. And then last we have water. Again, 2 nonmetals, Fe765. Hydrogen wants to be +1. So what does the oxygen have to be? -2. Oh, oxygen likes that, right? Oxygen likes being -2. Any questions about the oxidation states? Yeah.
So now we have to compare tin from one side to the other,
Mm-hmm.
and then compare the nitrogen from one side to the other.
Exactly. We're going to compare each element from the reactant side to the product side and see if or how their oxidation state changed. So the first element is tin, and so we see tin went from 0 to +4. Is that oxidation or reduction?
Oxidation.
It's oxidation.
Lost electrons.
Yeah, it lost electrons. It increased its oxidation state. Next element is hydrogen. Here's hydrogen, a +1. Over here, hydrogen's also a +1. Hydrogen didn't change its oxidation state. Let's look at nitrogen. Here's nitrogen +5. Nitrogen's +4. So nitrogen changed. Its oxidation state went down. Its oxidation state was reduced. So nitrogen is reduced. This is the reduction. Yeah.
So I saw that you compared the oxygens and hydrogens, but then let's say they were different. Wouldn't you have more than 2 different?
Yes, you could have more than one thing being oxidized and more than one thing being reduced. That is possible. I don't think you'll see any of those sorts of things in this class, but it can definitely happen. Here's oxygen is -2. Oxygen's all over the place over here, but it remains -2 in every place. So we are directed here to identify the element that is oxidized. So the element that is oxidized is tin. Tin is oxidation. Well, tin is oxidized. And the element that's being reduced is nitrogen. Not nitric acid, it's nitrogen. Nitrogen is reduced. Any questions?
So we don't count the subscripts from the oxygen on the product side?
The subscripts here tell us how many atoms of oxygen there are, right? And so we do consider that. We consider that when we identify what the oxidation state of the other things in that molecule are.
Okay, so when comparing it,
But over here, this 3 just tells me I have 3 oxygens. They're each -2. And this is still -2 and -2 and -2.
oh, okay, so we don't add them up.
No.
When we're comparing.
You don't add them up when you're comparing. No. That would be more difficult. So thankfully we don't have to do that. Any other questions? So oxidation reduction have to occur simultaneously. If something is losing electrons, there has to be something else gaining electrons. There's no homeless shelter for electrons. So they have to be passed from one thing to another. Okay, so we talk about things that are being oxidized and being reduced, but we also talk about oxidizing agents and reducing agents. So the reducing agent is the reactant that causes another thing to be reduced. It's not confusing at all. Yeah, it is. It's heck of confusing.
So it's the opposite, right? So
They're opposite, yeah. So the way I think of it is I think about Hollywood. So in Hollywood you have movie stars and you have their agents. The movie star stars in the movie. That's why we call them movie stars, right? What does the agent do? Does the agent star in the movie? No, the agent arranges for the movie star to star in the movie. Okay? So that's what these agents do. The reducing agent arranges or causes something else to be reduced. The oxidizing agent causes something else to be oxidized. It does that by being reduced itself. So the oxidizing agent gets reduced. The reducing agent gets oxidized. Yes.
The way you have it on the slide, though, looks like unless I'm reading it wrong, the reactant that reduces an element in another reactant is called the reducing agent. So then, oh, I see. The reducing agent is different.
Yeah.
So the oxidized element is the reducing agent,
Yes.
and the reduced element
Is the oxidizing agent.
Thank you.
Yes. And it is confusing, and I wouldn't choose to talk about it this way, but that's just how everybody does it, and so we just kind of have to go along with the program. So if you think about agents, movie agents, right, then you can maybe work your way through it. So we'll do some examples here. Determine whether or not each reaction is a redox reaction, and if it is, identify the oxidizing agent and the reducing agent. So the first thing is identifying, is this a redox reaction? There's a couple of different things you can look at. In general, if you have a metal element and a non-metal element reacting, it's going to be a redox reaction. So here we have the element lithium and the element chlorine, and they're reacting. When I look at this is an ionic compound that's being formed, and so I went from a lithium atom to a lithium ion, and so I can tell that electrons are being transferred because I had atoms and molecules and now I've got ions. So electrons must have done something. We could also look at oxidation states. So here we've got 0 and 0 because those are both elements. And in lithium chloride, we have actual ions, and so the oxidation states will be the same as the ion charges. So lithium would be +1, and chlorine will be -1. Same as their charges. So you can look at this from the standpoint of, did it gain or lose electrons? Or you can look at it as an increase or decrease in oxidation state. So the lithium went from 0 to +1, so it lost an electron, right? Oxidation is loss of electrons. This went from 0 to -1, it gained an electron. Reduction is gain of electrons. So oxidation is loss of electrons. This one's being oxidized. Because this one's being oxidized, that means it's the reducing agent. Okay? So then before I forget what I just said, lithium is a reducing agent. I'm just going to call it Ra. The chlorine gained an electron. Reduction is gain of electrons. It's reduced. It's the oxidizing agent. If I was answering this question on an exam, I would say all of those things to myself in my head. I think, if you're doing this all the time, which I do it every semester, but in between I don't do it. If you're doing it all the time, then you come to the point where you're just like, oh yeah, I can look at that and tell. But we're not going to be there. I'm not there, and I teach this class every semester. So then what you do is you find a way that you can just quickly, it took 30 seconds maybe, reason it out, and then that works every time. So oil rig, and the agent is the opposite. So any questions about number 1? Let's look at number 2. Is number 2 a redox reaction? Bless you. It is, right? So here we've got aluminum, the element, and here we have aluminum ions. Here we have tin ions and tin atoms. Their charges changed. That's got to be a redox reaction. Okay, so let's look at what happened to aluminum. Aluminum went from 0 to +3. Did it gain or lose electrons?
Gained electrons.
It lost electrons. Yeah, it's confusing, right?
Isn't the number on the top right, the 3 plus, isn't that the amount of electrons?
Well,
This is charge.
it's the amount of electrons that were lost or gained.
Okay.
Yeah. And so, if you find yourself getting that backwards, which is so easy to do, then maybe instead of gaining and losing electrons, it might be better to think of the oxidation states. Yeah, so this is 0 and this is +3. So it went up. It's oxidized. And this one's going from 2 to 0. It's going down, it's being reduced.
The oxidants.
And then the opposite agents. So aluminum is being oxidized. That means aluminum is the reducing agent. The tin going from 2, I guess I should write that in there, from +2 to 0 is being reduced, so it's the oxidizing agent. Now it's important that we've got aluminum as the reducing agent, pointer froze up, and not Al3+. It's got to be the reactants. So aluminum is the reducing agent, tin 2 is the oxidizing agent. You guys okay? Let's look at number 3. Is this a redox reaction?
Well, how do we know on first glance?
That's a good question. How do we know on first glance? Well, one of the things we can look at is, are things changing their charges? And here they are not. This is one of those precipitation reactions that we studied. So the ions come in and they swap partners, but they don't swap electrons. They're just changing partners. So the lead was +2 here, and it's +2 over there. Lithium is +1 here, it's +1 over there. Nitrate stays together, is -1. Chloride remains -1. Nobody's changing their charges. And if you go through and determine all the oxidation states, they aren't changing either. So this is not a redox reaction. So then we don't have to figure out what's going on. Any questions? This last one. Is this a redox reaction? This is harder to identify. Well, we have something reacting with oxygen. That means it's oxidation, right there. We have 2 nonmetal elements reacting with each other. That's going to be an oxidation reduction reaction. Redox reaction. So if none of that clicks with you, then just assign oxidation states and see. Well, what's the oxidation state for carbon? 0. And for O2? 0. So that's a molecule But the two atoms in the molecule are identical. What does oxygen like to be? Likes to be -2. But if we've got two identical oxygen atoms in this molecule, they both want to be -2. They're not going to be able to convince the other one to be +2. So they just say, well, okay, we'll both be 0. It's better than someone having to be +2. You can't have them be different. So in a given molecule, all the atoms of the same element will have the same oxidation state. So these have to be the same, so they've got to be 0. Then we've got CO2. Two nonmetals, Fe765. Fluorine, nope. Hydrogen, nope. Oxygen. Oxygen chooses -2. What's the carbon have to be? +4. There's one carbon and there's two oxygens. Each of the oxygens has a -2 oxidation state. Therefore, that one carbon has to be a +4 oxidation state. All the oxidation states add up to the charge on whatever it is. Okay, so is this a redox reaction? Yes, it is. Things are changing their oxidation states. So carbon is going from 0 to +4. What's that? Oxidation. It's going up, right? So if it's being oxidized, then carbon is the reducing agent. Here I have oxygen going from 0 to -2. Oxidation state is being reduced. That's a reduction. So oxygen, O2, is the oxidizing agent. Oxygen is the original oxidizing agent. That's where all this terminology came from. Something combined with oxygen is being oxidized.
So oxygen, usually if it's in there, it's going to be oxygen.
Yeah, if you have oxygen, elemental oxygen here, that's going to be the oxidizing agent. Definitely. Any questions? Yes. This is one of those things that you have to just be able to talk through it. I mean, on this one, you've got a 50-50 chance of guessing correctly, but, that's just not always a good idea. Okay, so combustion reactions are characterized by something reacting with oxygen to form one or more oxygen-containing compounds. Often this includes water. And combustion reactions also emit heat. I mean, why do we burn things other than it might be fun? Why do we burn gas in the grill? To make it hot, right? Combustion reactions give off heat.
Okay.
Yes?
Is it true that when metal rusts, that's considered a combustion reaction?
That is considered a combustion reaction, yeah. Metal rusting, iron rusting. Yeah. It's iron combining with oxygen. It's a redox reaction. It is combustion. It's just not what we think of as combustion. We think of stuff burning, right? But it is a combustion reaction. So here in this example, we've got natural gas, which is predominantly methane, reacting with oxygen. When you have compounds of carbon and hydrogen, and they might have oxygen in them, when those combust, they always form CO2 and water. I really need to get that written on a slide. Carbon, hydrogen, oxygen compound plus O2. Always you get the same products, CO2 and water. So stick that in your brain. So here we've got methane. There we go. Methane reacting with oxygen to form carbon dioxide and water. Here the oxidation states are done for us. Carbon is going from a -4 oxidation state to a +4. So carbon is being oxidized. The hydrogen is going from +1 to +1. It's not doing anything. The oxygen's going from 0 to -2 in both of these. So the oxygen's being reduced. The oxygen is the oxidizing agent. Any questions? Write a balanced equation for the complete combustion of liquid C2H5OH. So that is ethanol, which is the alcohol that we can drink. Somebody showed me a really cute sign yesterday. It said, for a chemist, alcohol is not a problem. It's a solution. Yes, it is. It's a mixture of ethanol and water and other stuff. It's a solution. Okay, complete combustion. Anytime you see combustion, that's reacting with oxygen. Combustion is burning. What do you need for wood to burn? There has to be air, right? And what's needed in the air is the oxygen. So we're going to write this formula plus O2. So we have C2H5OH, and we're told that's a liquid. Reacting with O2. What's the state of oxygen?
Gas.
It's a gas. And that's going to form, what are the products going to be? CO2 and water. So CO2, what's the state of CO2? It's a gas. And H2O, what state should we write for H2O? Normally we would say liquid. At room temperature it's a liquid. If this is a combustion, is it going to be at room temperature? No, it's going to be hot. So we should write water as a gas.
For every combustion, are we going to have CO2 and water on the other side?
For every combustion reaction where the thing that's burning contains carbon, hydrogen, and oxygen, or just carbon and hydrogen, the products will always be CO2 and water. So there we've got our reactants and our products. We need to balance the equation. So we can do this using my tally method, or we can just do it by inspection. Which method do you want to do?
Is that OH at the end?
That is OH. Yeah, that's an H. Anybody have a
Let's do inspection.
inspection? Okay. So balancing by inspection. I'm just going to start at the beginning. This O2, here I have oxygen, an element by itself, leave him for last, because you can adjust him without messing everything else up. So here I've got 2 carbons, and over here I only have 1. So if I put a 2 in front of CO2, I can have 2 carbons over there. So I'll do hydrogen next because I want to leave oxygen for the end. Here I've got 5 oxygens plus 1. I know it's kind of tricky there. It's written that way because that tells the chemist that this is an alcohol. If it was written differently, it might be an ester or something else. So 5 plus 1, I've got 6 hydrogens here. Over there, I've got 2. So if I put a 3 in front of the H2O, then I have 6 hydrogens on each side. Now I'm going to put a coefficient in front of the O2, and I can fix that one without messing everything else up. So make sure that you're counting correctly. Here I've got a total of 4 oxygens, and over here I have 3, right? So 4 plus 3 is 7. And if you just look at this, you're like, oh dang, it's got that odd even thing going on again. But look, there's 1 over here. So there's 1 oxygen here, and what I need for this to add up to 7 is I need this to be 6. And so I can take that and multiply it by 3. And there we have a balanced equation. Any questions?